Good evening, good morning, or good afternoon, depending on where you are in the world. We'd like to present to you my next lesson in Basic Electronics series. Now, before I mention that, I would like to mention that to you that if you haven't seen the first 18 lessons, I recommend that you do that first, simply because lessons are cumulative and foundational, and so you won't understand fully the concepts if you haven't seen the first 18. So unless you already understand the concepts, then I recommend you watch those first. But if you already have, let's then go ahead and proceed and continue with this video. Now, what we're going to learn for this lesson is about radio frequency. Now, this lesson is about discrete circuits for AM and FM broadcast receivers. This lesson mostly concentrates the use of digital communications using radio frequencies. So that will include AM and FM, which we'll talk about in a moment what those are. Now, just as a little disclaimer, as regarding to transmitters in the law, radio transmitters, although most countries allow for use of low power short range FM transmitters and allocate certain bands for use of the packet radio, you should check with your local regulations to make sure that you're not breaking the law by using any of these designs I'm going to mention to you of the schematics, etc. Now let's talk more about what AM versus FM is, starting with AM. Now AM stands for amplitude modulation. It all starts with AM transmissions, which use carrier frequency modulated by the audio signal that is being transmitted, which is being transmitted by, by the carrier frequency is only about 4.5 times the audio signal. That is in a real. So let's just say in a real. Oops, that I don't know why that did that. In a real AM broadcast, the audio signal will generally be a maximum of 16 kilohertz, that's 16,000 hertz, against a carrier frequency of 500 kilohertz, making at least 10 times as many cycles of carrier in each signal, of each cycle of the audio frequency shown. Now, the shown as in shown below. And what you have is a graphical representation of the AM signal. What you have is a y and x axis. So on the y axis, you have the amplitude of the signal. Going up is positive and going down is negative. And for time, the less of the time, and going down is less of the time. Going up is an increasing amount of time. So, in terms of our legend, which is what each one represents, the dotted represents the broadcast signal, and the dash represents the audio signal. And if you look at the graph here, you can understand that what can actually be heard by the human ear is represented in the blue. That's the audio signal. And you notice the audio signal is not as high as the broadcast signal in terms of what you can hear. So keep that in mind, that not everything you hear is what there is. And I meant to push this up more. Let's push this up more. This is kind of weird. Now, in terms of the AM transmission, what we want to say about this is that one of the reasons the quality of the AM is so bad is that there are many other factors that can affect the amplitude of the carrier, including atmospheric conditions or changing the positions of the receiver if you're listening in a moving vehicle. Okay. When it comes to receiver, you need to be able to separate the radio frequency, that's RF, from the audio signal. Now, the earliest AM receivers, that is crystal sets, were literally a coil antenna and a variable capacitor, that is diode, which is made out of germanium for its lower forward voltage and sensitive headphones. Improvements have been made for the design of AM receivers, in particular amplification of the RF signal before detection, followed by further amplification to drive a loudspeaker. But the basic principles in an AM receiver are as they were a century ago. So just to give you a quick little primer on the history, and how they went. It's not been much of a difference in the AM signal. And what we're hearing, what we're looking ahead of us, is a basic schematic of that. And when you look at it, first you've got to consider at the top, you have this diagram here that represents the antenna. And then when you go to, okay, so we have an antenna there. What's happening is we have a L represents the amplification of the sound signal. And then that's going in one path, which is going directly to its node that goes directly to ground. And then from where it's starting from its starting node to the next node would be the capacitor, and then going directly to diode, which will direct the current flow in one direction, and that will be the outputted. They'll give you the outputted power for the crystal earpiece, and of course, the crystal earpiece is also connected to ground. Now, that is a basic AM receiver. And unfortunately, I need to bring this up. This doesn't come out perfectly, but it's okay. The idea is we're getting the information out there for you, and that's the important thing. Now, when it comes to let's talk about FM and how this works. So, FM stands for frequency modulation. Now, frequency modulation, otherwise denoted as FM as the acronym, improves on AM by varying the frequency of the carrier rather than its amplitude. Now, what this does is it's immune from changes due to atmospheric conditions or movement of the receiver. How an audio signal would be used to modulate a carrier. Now, what we're looking at is, again, a similar graph. On the y-axis, we have the amplitude. So at 0 point, that's the midpoint. Going up, the y-axis is positive, and going down is negative. And what we're in from the middle point, when we go from left to right, that's time. So increase in time. So what we're doing when we look at the legend here, again, that is the key of what the symbols mean in terms of its color and meaning, is we're looking at a broadcast signal versus an audio signal. So we understand that the broadcast signal has less amplitude in between each and less variance versus an audio signal which has great variance. And that's denoting directly about the frequency modulation. Now you got to consider that extracting the audio signal from an FM broadcast can be accomplished by using a number of techniques, but perhaps the most common is to use what's called a VCO, an arrangement called a phase lockup loop. Now also keep in mind that VCO is as follows. Now VCO stands for voltage controlled oscillator. A voltage controlled oscillator, or VCO, is an electronic circuit that generates a periodic electronic signal whose frequency is controlled by an applied DC voltage. In other words, in simpler terms, a device that can produce a signal at a specific frequency, and that a frequency can be adjusted by changing the voltage input. Very important input, because it's how much is initially going through the circuit. Now, in terms of how it works, what you have first of all is an input voltage. This determines the frequency of the output signal. You also have, as a secondary component, you have an oscillator circuit, which is the core of the VCO, often consisting of a resonant circuit such as LC tank and the amplifier. The other component we have is called the frequency control. Now, this is the input voltage can alter the characteristics of the resonant circuit, for example, capacitance, that is, for example, what otherwise known as a capacitor, which can store voltage, therefore changing the frequency of oscillations. Now, when it comes to applications, we can consider the following. Actually, I wonder if I can just move this up a little bit. Okay, so I don't need that much space in between. In terms of applications, we have 4 main ones. First one, as we talked about, is the frequency modulation, that is FM. That's the input voltage that can be modulated with a signal to create FM radio waves. Remember, secondarily, there's something called the phase lock loops, or PLLs. This is VCOs are essential components in PLLs used in frequency synthesis and synchronization. And for our third part, we have synthesizers. That is, VCOs are used to generate various tones and sounds. And electronic music synthesizers, thus the synthesizer. That is to generate tones and sounds. That is the main purpose. Now, when we talk about radar systems, so VCOs can be used to generate frequency modulated signals for radar applications. So again, this is generate frequency modulated signals. Let's talk about its key characteristics. First of all, the frequency range. That is the range of the frequencies a VCO can produce. Number two is the sensitivity. How much the output frequency changes with a given change in input voltage. And third of all is the stability, how well the VCO maintains a consistent frequency over time. Now, remember that in essence, a VCO is a versatile component that allows for precise control of frequency in various electronic systems. Now, also remember that PLL is configured as the FM demodulator. I'm going to move this down a little bit. Now, here is an example of such thing where we look at the schematic to show this point. I think so specifically we're going to refer to the PLL, that is the phase lockup loop FM demodulator. So what we have essentially is the RF input, that's a radio frequency input, going to the phase detector. From the phase detector it goes to the low pass filter, and from the low pass filter it goes to the amplifier, that's to amplify the signal. And then you will have the demodulated, which is going from AM to FM. Okay. When you modulate it, you go to AM, and when you demodulate it, you go to FM. Okay, so that's a demodulated audio output. So it's the audio output that has been changed to FM, and it's going to VCO, and then the VCO goes back to the phase detector, and so on. Now, keep in mind some important things I'm going to talk about. Just to go a little bit more in detail, is that the RF signal is first tuned to a particular frequency as with an AM receiver. But then they demodulate the original audio. Oops, sorry, let me do that. You demodulate the original audio. Thus, the RF signal is fed into a phase comparator. Remember comparators to compare various, its purpose is to compare various voltages. Now, the phase comparator produces an input that if its input signals are completely in phase, the phase comparator produces an output that if its two input signals are completely in phase. That is, when you compare the 2 volts, if they're the same, it's in phase. If the signals are out of phase with each other, then the comparator produces an output proportional to the difference in phase. Why? Because both of the voltages are not the same. This signal is then low-pass filtered, amplified, and used to control a VCO, whose output supplies a second input to the phase comparator. Why? We want to see the voltage coming in. Okay. This feedback results in the VCO producing a signal of the same frequency as the RF input to the phase comparator. Now, if you think with common sense why this is important, we need to have the same frequency. We cannot have various frequencies. We need stability in the frequency by having a single frequency. As the output of the VCO tracks RF frequencies, the small shifts in phase resulting from the modulation will result in the audio signal being available in the filtered and amplified output of the phase detector. So technically that is where we have here for the amplifier. Okay. Now what we're doing is, let's talk more about, so next thing is our amplified output will contain demodulated audio signal almost as a side effect of the PLL tracking the broadcast signal. Then the PLL chips are available to include the VCO, phase comparator, and other parts of in one convenient package. However, if you're making the FM an FM receiver, and you'll need to use an FM receiver IC, which stands for, if you remember from before, this is integrated circuit or chip, right? Computer chip. That includes the RF amplification, PLL, and pretty much everything needed for the receiver aside from a few resistors, capacitors, and inductors is in that IC for the PLL. Now, what you need to remember from the following is that when we consider phase-locked loops, or PLLs, you need to remember that PLLs is an electronic circuit that synchronizes an output signal. The important thing is synchronize an output signal, okay, to a reference signal. So when we synchronize, it means we're on the same one. We have the same thing. They're widely used as of various electronic applications, including frequency synthesis, data recovery, and clock generation. These are some applications which I won't go over for the purpose of this video. Now let's talk about some components of a PLL. For the PLL, you have the voltage control oscillator, which is the main part, that's VCO, generates an output signal whose frequency can be controlled by an applied voltage. Then after that, you have a phase detector, or PD, compares the phase difference between the VCO's output and the reference signal. After that, you have a low phase filter, low pass filter, or LPF, smooths out the output of the phase detector, providing a DC voltage. Okay. Then we have a loop amplifier, and it amplifies the amount of LPF to control the VCO's frequency. Now let's talk about how this PLL is going to work. It's going to work by number one, by its phase comparison. That is, the phase detector compares the phase difference between VCO's output and the reference signal. Remember that for the error signal, if there's a phase difference, the error signal is generated. Frequency adjustment. Error signal is amplified and fed to the VCO, causing it adjust its frequency to match the reference signal. And then we have the phase lock, which is the PLL continues to adjust the VCO's frequency until the phase difference is minimized, achieving the phase lock state. Now let's talk about our applications of PLL. That is, first of all, it's a frequency synthesis, generating precise frequency for applications like radio transmitters, receivers, and synthesizers. It's also for data recovery, that is, clock recovery and digital communication systems where a clock signal is extracted from the data stream, which is a whole other topic, but just talk about this on the basic surface level. We also have a frequency conversion, which is converting a signal from one frequency to another. So that would basically, if I understand this right, this would be from AM to FM signal. Then we have the phase modulation, which is modulating the carrier signal with phase modulating signal. And then, of course, we have a synchronization, which is ensuring synchronization between different devices or systems. Now, here are some advantages of using PLLs. Number one, we have high accuracy. PLLs can achieve very precise frequency control. We have versatility. They can be used in a wide range of applications, that we just saw earlier. Also, it has efficiency, which is PLLs are often more efficient than frequency generation methods. So, in essence, a PLL is a powerful tool for controlling and synchronizing frequencies and electronic systems. So keep that in mind. Now let's talk about the digital radio. As you know, radio is now a much more digital affair. So it's usually, because we're dealing with FM, so you have your FM radio receivers and transmitters are now implemented as software-defined radios, or SDRs, which is another topic. That's what it's called. Processors are now fast that with a very small amount of hardware, they can produce and decode analog broadcast signals in software, so you can use software to do it. Now, keep in mind that you want to make a short-range FM transmitter that will transmit the sound signal to a domestic FM frequency, where it can be received on a household receiver. Okay, so you want to start from A and decode it to B. Right, you have that you need to be able to make that the household receiver be able to pick up the FM signal. So what you want to do is you want to use a frequency VCO chip, which is named MAX2606. That's capital M, capital A, capital X. Set to operate in a frequency of the FM band and use the audio signal to make small adjustments to the frequency. And here you can see the actual schematic here. What we're having here is, as we said before, when we look at the schematic, we won't want to look at it on the larger parts and then the smaller supporting parts. So what we look at is the audio, we look at the chip, and then we look at the antenna. So what we're doing is we're looking at our point where it goes in the resistance and indirectly to ground. That's from our audio, so it has for capacitor. Then we have our pin outs from the IC. So we have first one is IND, then we have ground, goes directly to ground, of course. Then we have the tuner, which is going to go, this is the third pin out, which is going to go to our capacitor, and then directly to ground. Then we look at, we look at 4, that's going out, going through resistor 2. Okay, and then connecting with the going with pin out 5 going out. And then from continuing on, so that's like one main path, and then there's a second intersecting path. The other main path, the main path is going to resistor 1, connecting to going out to the antenna. And then there's a capacitor to store the charge, and then the antenna for the signal going out. And that's basically what that is. And that's an FM transmitter using the VCO IC, standing for integrated circuit, or the chip itself here. Keep in mind that the antenna can be a telescopic FM antenna or simply just a few feet of wire. So it depends on what your needs are, depends on how you do it. I'm going to close this here. Now let's give you an example of what you can do with this. What you want to do is you want to build an Arduino powered FM receiver. Remember, receiver just receives a signal, it doesn't transmit the signal. If you want to do both, that's called a transceiver, which means it can transmit or send out a signal, and it can receive. But in this case, we're only talking about a receiver that uses FM signal. Now you want to make an FM radio receiver controlled by an Arduino. This is a main board. I'll show you a picture in a moment. You have two main ones. You have one called an Arduino, and then one called a Raspberry Pi, as in PI. What you want to use is a TEA5767 FM radio receiver module controlled by an Arduino and other connect headphones or a power amplifier to drive speakers. Right? Because you have very low sound up input, what they'll do is they'll take and that will amplify the sound. Here's a basic schematic of what we're dealing with, and again, what we want to do just as a good form, we want to look at the major parts of the schematic first, then look at the supporting parts second. So what we have immediately is we have the Arduino Uno main board, and then we have the IC. Now, in between the Uno and the Arduino Uno and the IC, we want to look at any pinouts from the IC, and then the current flow of the voltage. So we have 5 volts of voltage going through that, and we have basically we have 3 major ways, okay? Because we see the 3 pinouts going out. The first one is 5 volts coming into the circuit, going through resistor 1, and going to the first pinout, which is SCL. And then on the second node, so after resistance 1, we have that one node where it stops and goes directly to SCL. The second one is going through resistor 2, so meanwhile it's slowing down the current flow. And that's going to SDA, which is the second pinout. And that's going to go directly to our antenna through our chip called TEA5767. And then also we have a pinout from this Arduino called SCL that will be passed after it's gone through that would be interconnecting with the other main path that went through resistance 1, goes through SCL, and then from there goes through the chip. Now consider that also with this, of course, we have the two main pinouts. One is 5 volts going out into our resistors and to the IC, and the second one is our ground going directly to ground. Now when we have this, we also have other pinouts. We have mode that will go directly to the node and directly to ground. And we also have the one that goes in directly for 5 volts to power this chip. And that will go directly to ground. Now, before we finish this, we need to understand also that we have to consider left and right for sound going out to the power amp if you're not using earbuds or earphones of sorts. And that is connecting, and I'm going to move this up here. That is connecting a TEA5767 FM receiver module to Arduino. And this is an actual picture of that. Notice we have an Arduino as our main board, and then we have the white breadboard connected to our main chip here. That will give you the signal. So we have something that's going out. We have our sound ports going out. We have the chip connecting to that. And then we have our pass going to each pin that's going to that particular sound. Okay, so this is their breadboard's going to be your go-between to execute the functions of the Arduino. And that's an Arduino controlled FM radio on the breadboard. Now, when we want to send digital data over a radio, you want to send data hundreds of yards over a radio connection. Okay, so this is going to be a certain distance away, and that will require a certain amount of power output. Now what you want to do is you want to use a CC1101 RF transceiver that is, as I told you before, being able to transmit a signal and to receive a signal, otherwise known as a transmitter and a receiver, combined together called a transceiver. Now what we have is, again, major components of this schematic. What we're dealing with is the Arduino Uno, and we're dealing with the IC. Now the IC needs to be connected to a power source, so it's going to be connected to that breadboard. And what we're doing is, which I think, do I have a picture? Yeah, I'm going to show you later. This is basically what it is. So this is basically a schematic of what this physically would be. Now, let's talk about our schematic of how this works. Is we have 3.3 volts DC coming in, and then in this we look at the two major paths, which is going into the chip, and the other one is going directly to ground. You see ground. Now, so we know that when we go to 3.3 volts, we're going to the IC, which is CC1101 module, to VDD. Okay, going into that chip. Okay. And then we also notice on this chip we have diodes, denoted by capital D. So it's diode 2, diode 13, diode 12, diode 11. The purpose of them, as I said in one of the earliest of my videos, is that the purpose of diode is to redirect or control the direction of the current flow. So what we're doing with diode 2 is we're going to go, if we logically follow the line, it's going to the chip called GD00. We go to diode 13. We notice from here, we're going to go through resistance 5 and then go to a acronym of SCK on the IC chip. And then we can go to diode 12. We're going to see that goes to MISO, which is a function on the IC. And we go to diode 10. We're going to go, the diode 10 will go through a resistance, which will end up with a node that go to CS, and also will go to resistance 4, which will go past resistance 1 and then also to ground. And then finally, when we have diode 11, we're going to go through resistance 2, which goes to MOSI and SCK. Okay, and then you'll see that path. And then also diode 1 going past resistance 2 in node, instead of going into MOSI, it also can go to resistance 1, and then from resistance 1 it'll go directly to ground. So you can see how it has the two major paths, each subpass based upon how it's connecting to the CC1101 module, which is your integrated circuit module. And that is wiring for a CC1101 module to an Arduino. And ahead of you, you see the actual picture of what the schematic was describing. Now, keep in mind that this main board needs to be connected to the breadboard in that particular configuration to have it work according to how the schematic was describing. Okay, so that will do it for, and of course that's an Arduino Uno wired to a CC1101 module. Alright, now that I have that set, I'd like to first of all thank you for taking the time to watch this video, as you could be watching any other electronics video, but you're watching mine, and I greatly appreciate it because of that. While this did provide value for you, what I'd like you to do is please click like on the video. That way it'll be pushed through the algorithm and more people will be able to view it and enjoy it. If you haven't already, please click the subscribe button. That way you'll have access to all the content on my channel, as I certainly do have a variety of topics on this channel that you can benefit and learn from. Also, if you haven't already, please click the bell button. That way you'll be notified of all my future videos. That way you won't miss any of my future videos or new videos, because you'll be notified accordingly. So, I'd like to wish you a great day wherever you are in the world. Take care, and I'll talk to you next time. Bye for now.